10. So it's been 11 years since we know each other, and I'm glad that the collaboration is continuing.
Yeah.
So I'll share my screen in the meantime. Desktop 2 and okay, cancel. And I hope you can see my slides.
Yes.
Okay, awesome. Okay, so as Sarah said, I'm an experimental petrologist, just like her. So basically, I use high pressure temperature equipment in our group to simulate conditions in the interior of the Earth and other planetary bodies, and the planetary bodies include the moon as well. So the topic of my presentation today is how hot and wet is our moon, and what can we learn about that from experiments? Before I even go into details, I will probably disappoint you a little bit by saying that we do not have definite answers to either of these questions yet. But as with anything in science, we are making progress. So my talk today will be about what is being done what has been done and what is being currently done in our research group to tackle these questions. And I also want to acknowledge my collaborators who have been invaluable in tackling some of these questions. Okay, so the first obvious question is, why even care about the moon? As we all know, that the Earth and the moon, they had a common origin. Supposedly a Mars-sized body called Theia slammed into the Earth, and then there was a very high energy process where things were vaporized, there was silicate vapor, and then condensation of that, and then from that we had the moon and the Earth forming. So owing to the common origin of these two and the fact that the moon is our closest neighbor in the solar system, learning about the moon can even tell us something about our own origins here on the Earth. Now, as with any planetary body, one of the fundamental questions is, how hot is that body? So how hot is the moon? As I just said, that because of this giant impact, it was very hot initially, of course, and a substantial part of the moon was completely molten. So we had a magma ocean that formed after the giant impact. And then with time, this magma ocean cooled down, and then it crystallized minerals that formed the solid body of the moon. So these columns here, they show the different mineralogical stratigraphy that we think formed the solid body of the moon after it crystallized from the magma ocean. And these have been determined by experimental studies as well as by thermodynamic modeling. So what you can see here is that if I look at the acronym, so OL is basically olivine, OPX is orthopyroxene, CPX is clinopyroxene, plage is plagioclase. So a lot of these very familiar minerals are actually similar to what we have in the upper mantle of the Earth. So broadly, if you observe here, the moon's mantle is basically an olivine pyroxene bearing body, with some special minerals coming in towards the very top, which includes plagioclase, ilmenite, and then a quartz-bearing phase. So we have a fair bit of idea about what the moon must have been, the internal structure of the moon must have been after it crystallized from the magma ocean. Now, what about the moon's interior today? Like, has it changed? Has it evolved since the magma ocean cooled down? And really, in order to constrain what the present day interior structure and composition of the moon would be, we need to constrain the thermal profile of the moon really well. So this is a temperature in Kelvin versus depth plot. And this gray region here actually show the range of selenotherms that have been derived for the present day moon. Selenotherm is basically the equivalent of geotherm for the moon. As you can see that there's a wide range here. This gray bar, it's pretty broad. So there's about a difference of 800 degrees, 800 Kelvin, which is substantial. And I just want to show you a little bit here. So the cyan or the blue dashed line here is the minimum estimate. And then this red one here is the maximum estimate, what we call max T. And then this yellow line here is the sort of the average or the mean, what we call the mean T. Now, because of this wide range of estimates of thermal profile within the lunar interior today, if we try to derive the mineralogical profile, there's also a difference for that. So this figure is a busy one, but I'm just going to quickly walk you through this and just tell you what the upshot is. So all these columns that you see are basically different layers of the moon. So if the moon were made of a core, which would be these bottom layers, and then a few mantle layers, and then there's an upper ilmenite layer, which is an iron titanium rich layer. I'll talk about that later in the talk. And then you have the crust, which is basically mostly anorthite, plagioclase bearing crust. And then what we did in this study is actually we used the mass and moment of inertia of the moon as a constraint to see that what kind of mineralogical profile or stratigraphy would best explain the mass and moment of inertia of the moon in order to get a handle on what the moon's interior structure today would be like. So this panel at the top is basically a z-score. All I'm going to say is that the lower is the z-score, the better that profile's fit is with the mass and moment of inertia. And all these profiles are the top 30 models that we found from the study. So, and then these diamonds here, the color codes are basically based on the thermal profiles that they represent. So anything with a red diamond is for the hottest thermal profile, anything for the yellow is for the mean, and then anything with the blue is for the colder profile. So as you can see that which profile fits best with the mass and moment of inertia really depends on the thermal state. So right now we have stratigraphies all over the place, the hottest ones and the coldest ones with different stratigraphies that would explain the mass and moment of inertia. But then in order to really get a handle on what's the best profile for the present day moon, we need to narrow down what the selenotherm is. And that sort of points out why the selenotherm, why is it so important to constrain the selenotherm so well. So then, of course, the question is, how do we constrain the selenotherm better? Now, before I go into details of how we took an attempt of constraining the selenotherm better, I will point out a couple of observations about the moon that were useful in this. So the first observation comes from Apollo samples. So there were these pristine lunar glasses that were brought back from these different Apollo missions. So this is iron oxide versus titanium oxide. All of these color-coded bold symbols are the Apollo samples. And then just for reference, the gray ones here are basically mid-ocean ridge basalts and ocean island basalts from the Earth. So you can see that these Apollo samples, these pristine lunar glasses, they are very distinct in composition from terrestrial glasses. They have very high iron, and they have a range of titanium concentrations over here. And some of them actually have very high titanium oxide concentrations, which is not observed in terrestrial magmas. So then, of course, the question is, at what could be the source of these sort of very distinct, unique magmas that were found on the moon? So Tim Grove at MIT, him and his group, they've been working on this for several years now. And they did some experiments where they did something what we call a multiple saturation experiment to try and derive the depth of the source of these magmas. And what they found is that these particular magmas, which form these lunar glasses, they were sourced from a range of depths in the lunar mantle, but including some that were a few hundred kilometers deep. So now, of course, the question is, what would cause some of these very high titanium, high iron magmas to form at that depth in the lunar mantle? Because if we go back to the stratigraphy that we know from the lunar magma ocean crystallization, if you look at these depths here, what we see is basically olivine and pyroxene, and none of these olivines or pyroxenes have high enough iron or titanium in them to really explain the formation of these very unique magmas. The only high iron titanium bearing layer that we predict would form from the lunar magma ocean crystallization models is this very late stage layer where we have this mineral ilmenite crystallizing. Ilmenite is an oxide with basically iron and titanium in it. So this is the only layer that forms, that too, at the very shallow end of the magma ocean, that has substantial amount of iron and titanium to explain the source of some of these magmas. But then how do you explain the presence of this layer at depths to actually form sources for these pristine lunar glasses? So as it turns out, this particular layer, because of its high iron and titanium content, is actually denser than the underlying mantle. And so if you have a denser layer sitting on top of a layer that is, or layers that are less dense, they will likely form instabilities and actually sink into the mantle. And this is what we think must have happened at some point in very early on in lunar history, what we call the lunar mantle overturn, where this high iron titanium layer basically sank deep into the mantle because of its density. And that is one process that could introduce these high iron titanium layers or iron titanium bearing lithologies deep inside the lunar mantle, which could eventually be sources for those very unique glasses that we found from the Apollo mission. Okay, the second observation, and this comes from geophysics, is upon inversion of the seismic data from the Apollo missions, this paper by René Weber et al., they concluded that in order to explain the seismic velocities, there has to be a partially molten layer sitting at the core mantle boundary of the moon. So at depths of between something between 1,200 to 1,400 kilometers. And they predicted that this partially molten layer would have somewhere between 5 to 30% partial melt. Now, the question is, what would cause this layer to be partially molten at that depth? Could it be related to the overturn process? So is it possible that the overturned iron titanium rich bearing layer, as it sank deep inside the moon, actually partially melted to form that partially molten layer sitting at the core mantle boundary today? But in order to really test that hypothesis, the first thing that we need to do is constrain the partial melting behavior of this iron titanium rich layer. And once we constrain the partial melting behavior, we'll know what temperature range would produce this 5 to 30% partial melt. And that in turn can give us a handle on what the core mantle boundary temperature of the moon could be. And then that constraint could be used to derive the selenotherm of the moon. So what we've done here is basically experimentally constrain the melting behavior, the melting temperature, as well as the partial melting behavior of this high iron titanium bearing layer if it were to sink near the core mantle boundary of the moon, or even in the lunar mantle. So in order to do these experiments, what we did was we synthesized these analogs of high iron titanium composition from previous studies. So we synthesized two different compositions, one that was just the pure iron titanium rich composition that we expect would have crystallized from the magma ocean, and then another one where we actually mixed that layer with some of the lunar mantle, because it's possible that there could be some mixing between the lunar mantle and this iron titanium rich layer. So we had two different starting compositions. And then what we did was we used this instrument called a multi-anvil at Bayerisches Geoinstitut in Germany, where I was affiliated a few years ago. So what we did was we used the starting composition to, and then subject that to high pressures and temperatures that we would expect inside the lunar interior, and then across a range of temperatures to see what kind of partial melt do we get, what kind of mineralogical residue do we get. Basically, what is the phase equilibria of this high iron titanium rich composition in the lunar interior. So the experiments were performed at two different pressures. A shallower pressure, which would be the expected conditions for the sources of the lunar glasses, and then also a deeper pressure, which is closer to the core mantle boundary of the moon. And then once we did these experiments, so we cooked these starting materials at these high pressure temperature conditions, we looked at what we obtained. So these are some of the results from two different experiments. The one to the left here is actually an experiment which was done using just that high iron titanium rich composition. And then the one to the right is actually one where we had a mixture of that iron titanium rich composition with a lunar mantle composition. So what we observe is that we have this a melt layer, which so the melt basically quenched to a glass, because we quench our samples and then we take out the quenched product and study them. So anything that was a magma or a liquid at that high temperature condition quenches to a glass or a quenched matrix, depending on the melt composition. So we had glass, we had iron metal saturated, we had augite, so very iron-rich pyroxenes, and then we also had some quartz. And then when we looked at the mixture of this high iron titanium composition with the lunar mantle, we see a lot of quenched melt here. And then we also see iron metal saturation. And then we find orthopyroxene and olivine, which would be expected in the lunar mantle. So basically, when what we did was we ran these experiments at a range of pressure temperature conditions. And upon doing that, we were able to derive what the solidus temperature of that bulk composition would be. So the solidus temperature is the temperature at which these compositions would basically initiate partial melting. So these curves here, the red and the blue curves, these are the two compositions for these experiments. So the red one is the pure iron titanium rich one, and the blue one is a mixture of that iron titanium rich composition with a mantle. Just for reference, this pink curve here is the solidus for peridotite, which is what our Earth's upper mantle is made of. And then this green curve here is the solidus of an olivine-rich lithology. So as you can see that compared to what typical olivine pyroxene-rich lithology would be, these high iron titanium-rich compositions actually have a lower melting temperature. So that means that it is possible that they could actually contribute to this partial melt that's sitting at the core mantle boundary of the moon today, without that layer being extremely hot, so that it would actually have to be above the solidus of, let's say, just an olivine and orthopyroxene bearing mantle. So now, of course, the question is, if these iron titanium rich cumulates are responsible for the partial melt at the core mantle boundary of the moon, that partial melt has to be dense enough to be stable at that depth, because if it's not dense enough, then it would actually rise. So the next thing that we did was actually estimate the density of these partial melt compositions. So for that, we used the Birch-Moynihan equation of state. And I'm just going to quickly go through these to make sure that all of you are on the same page as far as the symbols are concerned. So this is pressure, that's P. And then we have the isothermal bulk modulus, the pressure derivative of the bulk modulus, and then the densities, which is basically what we want to find out. So we use the Birch-Moynihan equation to estimate the density of these partial melts from the experiments, and this is what we find. So this is density versus pressure, and then this black line here is the equivalent of PREM for the moon. So it's the very preliminary reference model for the moon. And then the range of densities that we find for these liquid compositions actually span all the way from less than what the mantle would be to basically greater than what the mantle density would be. So right now the density range, gives us something that's inconclusive. So these melts that would form in the lunar interior from these high iron titanium rich layers, they could either sink if they're denser, or they could rise. So either one of them. So basically, in a future study, what we're looking at right now is constraining the densities of these melts better using experiments. But in any case, for the two scenarios, one where the partial melt density is higher than the surrounding mantle, and it's probably neutrally buoyant near the core mantle boundary, that's when those partial melts can actually contribute to that partially molten layer that we think resides at the core mantle boundary of the moon today. And then this other scenario is where the partial melt basically is less dense. And so once it forms, it will just rise up and then maybe contribute to magmatism on the moon. But if, let's say, the first scenario were true, that is, these melts are actually denser than most of the lunar mantle, or they're neutrally buoyant at the core mantle boundary, then they can contribute to the partial melt at the core mantle boundary, which means we can use the melting properties to constrain the core mantle boundary temperature. So from the seismic studies, the prediction is that there's about 5 to 30% partial melt sitting at the core mantle boundary. So from our experiments, we were able to find out that 5 to 30% partial melt would actually correspond to about 1330 to 1470 degrees Celsius at the core mantle boundary. So that's right here, this gray bar right here. So if these melts end up being dense enough that they would be neutrally buoyant at the core mantle boundary, then we can actually use the melting property and get a constraint on what the core mantle boundary temperature would be. And currently, we're actually working on deriving a selenotherm using this constraint so that we can get a better handle on what the thermal state of the moon is. So the summary so far is that the partial melting of these overturned iron titanium-rich cumulates and their mixture with the mantle was basically performed at these two different pressure conditions in the moon's interior and a range of temperature conditions. The estimated densities of these partial melts, well, we estimated the densities, but then the densities ended up either being higher or lower. So basically the fate of these melts at the moment, they're inconclusive. And so we have an ongoing study to constrain the densities better. But if these partial melts end up being denser than the mantle or neutrally buoyant at the core mantle boundary, then 5 to 30% of partial melt would stabilize between this temperature range of 1330 to 1470 degrees. And this would be a constraint on the core mantle boundary temperature of the moon. And then the core mantle boundary temperature of the moon can be used as a constraint or a boundary condition for constructing the selenotherm, which is again a future study that we're considering. So this is sort of the first part of the talk about how hot the moon is and what we know and what we're doing to tackle that question. So now I'm going to move to the second part of the talk, which is how wet is the moon? Now, when we talk about the moon being wet, it's not soaking wet. It does not have a water ocean. We all know that. But there have been measurements of basically hydrogen present in some of the lunar materials, and I'll talk about that soon. But of course, the first question is, why even care about how much hydrogen there could be on the moon? So the bulk hydrogen, along with the deuterium hydrogen ratio in the bulk silicate moon, it can be useful because it can be used as a constraint, A, to derive the dynamics of the giant impact. So in order to retain X amount of hydrogen in the moon, what kind of dynamics, what kind of energetics will be required for the giant impact? And of course, the second thing is determine the origin of volatiles in the Earth-Moon system. So was hydrogen in the Earth-Moon system derived from these chondrites, volatile rich carbonaceous chondrites or enstatite chondrites, or were there other sources? So basically, that can be used to derive the nature of building blocks of the Earth-Moon system. So this sort of underscores the importance of constraining the bulk hydrogen content of the moon. Recently, as I said, that hydrogen has been measured in certain lunar samples, and they include a bunch of samples such as olivine-hosted melt inclusions, glass beads, apatites, plagioclase grains, granite clasts. And based on the measurements on all of these lunar samples, currently, the estimate of the bulk silicate moon water content is actually a wide range. It could be anywhere from tens to hundreds of ppms of hydrogen. There's even one estimate which says that the moon is so dry that it has about like 1 parts per billion of hydrogen, but I think that's an extreme one. Other than that, the range basically spans orders of magnitude. And just for reference, the estimate for bulk silicate Earth right now is about 500 to 1,000 parts per million. So can we basically constrain the bulk water? So when I say water content, I don't exactly mean water, but what I mean is the water equivalent of hydrogen concentration. It's just the way it's expressed. So can we constrain the water content of the moon better? So recently there was this study, actually a few years ago now, Hui et al. This is a figure from their paper where they measured the water content in certain lunar samples. Actually, they measured the water content in these ferron and orthosite samples. And I'm going to just right now show you exactly where that is. So this here is a sequence from, let's say, the lunar magma ocean crystallization. So at the bottom is what crystallized first. And then as you go to the top, this is what crystallized later. So At the bottom, when it says 0, that means that's the first thing that crystallized from the magma ocean. And then as you keep stacking things on the top, 100% is the last thing that crystallized from the lunar magma ocean. So measurements of water have been done on several of these samples that we think are basically parts of lunar magma ocean that have been exposed on the moon. So there's these olivine clasts right here. So that's basically what it is. So this here is the water concentration in parts per million versus age. So this is where the olivine clasts lie. And then we have some pyroxene samples, which probably crystallize somewhere here. And that's the water content that's measured for that. And in this particular study, Hui et al., they actually measured the ferron anorthosites, which are part of the flotation crust on the moon. And then there are some creep samples, which are these sort of very potassium rare earth element and phosphorus rich signature that we see on some lunar samples. And then the water contents for those were measured as well. And then these are basically a lot of like basalts whose water contents were also measured. And then using the water contents of all these different lunar samples, this study came up with the bulk water concentration of the lunar magma ocean, which is sort of representative of the bulk water concentration of the bulk MOOC itself. But in going from concentrations in these different lunar materials obtained from different sequences in the lunar magma ocean crystallization to deriving a bulk water content of the lunar magma ocean, there is an assumption that goes in there. And that assumption is basically what we call the partition coefficient of hydrogen. So the partition coefficient of hydrogen is the concentration of hydrogen in the mineral over the concentration of hydrogen in the liquid. So if hydrogen is very compatible in the mineral structure, then the DH value or the partition coefficient would be high, greater than 1. Whereas if DH is less than 1, that means basically hydrogen prefers to go into the melt over the mineral. And this value has to be assumed in order to model how much the bulk lunar magma ocean, how much hydrogen would that have? Now, if we look at the range of partition coefficients of hydrogen for these different minerals that are relevant for the lunar magma ocean crystallization, what we see is that there's a range in estimates. The range actually spans across even a couple orders of magnitude. Most of these are actually for terrestrial materials, except for this one data for plagioclase by Lin et al., which is, these were experiments that were done for specifically lunar conditions. But other than that, all of these are for terrestrial conditions. But even then, you can see that there is a range here. So what we wanted to test was if there's a range in the partition coefficient of hydrogen, what effect does the partition coefficient of hydrogen have on estimating the bulk lunar water estimates, right? And again, as I said, that basically when I say the bulk lunar water, what I mean is the water that is dissolved in the solid moon as the lunar magma ocean crystallizes. So the objective of this exercise that we did, or we are doing right now, is to assess the importance of partition coefficient of hydrogen on determining the bulk lunar water content. And in doing so, what we did was we varied a few parameters. We varied the partition coefficient because we have a range that's available in literature. We varied the bulk water to start with. We varied the amount of interstitial liquid as the magma ocean crystallizes. And then we also varied the magma ocean depths. And then we modeled crystallization of the lunar magma ocean. And then what we are trying to see here is that in order to explain the amount of water that was measured in these ferron and anorthosite samples, how much bulk water do we need in the lunar magma ocean to begin with? And that would give us an estimate of what the bulk lunar, the bulk water on the silicate moon would be. Also, oh, sorry. Okay. Also, we considered a couple of scenarios when it comes to crystallization of the lunar magma ocean. Of course, there are volatiles dissolved, which means there's also degassing involved. And so we are examining two different end members here. One is an end member where as the lunar magma ocean crystallizes, of course, the amount of volatiles in the residual liquid increase, and at some point it would basically cross the solubility limit, and then you would have bubble formation. But then if the magma ocean is vigorously convecting, then once the bubbles are formed, these bubbles can even be basically dragged down to depths and resorbed. So in other words, this is an end member scenario where in a vigorously convecting magma ocean, there is no net degassing because the bubbles are all resorbed. On the other hand, there's this other end member where we consider a static magma ocean, where as the magma ocean crystallizes and we exceed the solubility threshold, we have bubble formation and the bubbles basically continuously efficiently degas. So we are looking at these two end member scenarios. This is an ongoing study. So right now I only have results from one scenario, which is the no degassing scenario. And that's what I'm going to present today. But before I even go into the results, I do want to tell you that the hydrogen in this lunar magma ocean is actually dissolved in two species. One is as water, and the other is as probably molecular hydrogen because it's reduced enough. So some of the hydrogen would be present as molecular hydrogen. So what we want to see is in this modeling exercise that what is the effect of partition coefficient on the bulk lunar water estimates. So this is a modeling exercise that was done by my graduate student, Arkadeep Roy, whose doctoral thesis this is a part of. So what Arkadeep did was he took the lunar magma ocean crystallization stratigraphy from this recent study by Charlier et al. And as he crystallized the lunar magma ocean, he partitioned the hydrogen into these minerals and the residual liquid through the process. And so this is sort of the figure that captures the results from his modeling exercise. So this is concentration of water in the x-axis and the radius of the moon on the y-axis. The surface of the moon is at the top. So basically the depth is at the bottom. So this is depth right here. These different curves here, so the blue curves represent the water content in the cumulates, in the minerals that crystallize. And then the red curve here is basically the water content of the liquid as you crystallize the magma ocean. So also the bold curves here are for higher bulk water content, so about 1000 ppm of water to start with. And the thinner curves here are for a lower bulk water content, so 100 ppm of water to start with. And then the solid curves here are for the lower estimate of the partition coefficient, and these dashed curves here are for the higher estimate of partition coefficient. And this black bar here is basically the water content that has been measured for these Ferroan and anorthosite samples by Hui et al. So as you can see that in order to explain the water content of these Ferroan and anorthosites the best, it's best explained by a much water-rich magma ocean, so about 1000 ppm of water, and where hydrogen is actually more incompatible. So in other words, the partition coefficient is at the lower end. However, that recent study by Lin et al., they actually measured a partition coefficient that was higher for lunar plagioclase under lunar conditions. So in other words, their argument is that for a reduced body such as the moon, hydrogen would actually be more compatible in minerals than in terrestrial conditions, in which case it is likely that the partition coefficients applicable for the moon are actually at the higher end. But in order to explain these water contents of Ferroan and anorthosites with a higher end of the partition coefficient, we basically need a very dry moon. So the upshot from this exercise is that in order to really constrain the bulk water content of the moon, we need to constrain the partition coefficient of hydrogen between the liquid and these different minerals in the lunar magma ocean crystallization stratigraphy much better. And so these partition coefficients need to be determined experimentally. And this is what the ongoing study in our group is right now. Again, in this modeling exercise, we also explored the effect of the depth of magma ocean and the fraction of interstitial liquid on the water content in plagioclase. So these are two different figures here. The one to the left is for a shallower magma ocean, which is only 600 kilometers deep. And the one to the right here is for a deeper magma ocean, which is about 1350 kilometers deep. So it's deeper, yeah. And then on the x-axis, we have the fraction of trapped liquid or interstitial liquid. And then on the y-axis, we have water content in plagioclase right here. So This orange bar here is the water content in plagioclase that has been measured in the ferron and orthosite suites and also the magnesium suites by the papers from Hui et al. And what we try to see is that as we crystallize the magma ocean in our models, what is the hydrogen content that we obtain in the plagioclase in our models? So these different curves here are for different water content. So the blue curves are for higher bulk water, and the orange ones are for, the blue curves are for the lower bulk water content, and the orange ones are for higher bulk water content. The dashed curves here are for the higher end of partition coefficient, and the solid curves here are actually for the lower end of partition coefficient. So again, from this exercise, what we see is that the fraction of trapped liquid is not that important, because these curves, the slopes are actually pretty parallel to the x-axis. But what is important here is actually the partition coefficients themselves. So far from this exercise, we see that actually when the partition coefficients are the lower end, that explains the water in plagioclase better. But if it turns out that from our experiments, we find that the partition coefficients are actually on the higher end, then the only way to explain the water in plagioclase is for a much drier moon. So that would mean that the moon is actually much drier than what we assumed in these models. So again, the summary so far from this part of the talk is that the partition coefficient of hydrogen, which is the ratio of the concentration of hydrogen in the minerals over the concentration of hydrogen in the melt, needs to be constrained better under lunar conditions in order to constrain the bulk water in silicate moon. And this is where our ongoing study comes in, because we are performing experiments to constrain the partition coefficient better. So far, our modeling exercise shows that the water content in the ferron and orthosites and the magnesium suites, the plagioclase in these lithologies, they're best matched by the partition coefficient at the lower end. However, if the partition coefficients end up being at the higher end, if that's what our experiments show, then the lunar magma ocean should be drier than 100 ppm of water equivalent. And also in future models, we will consider degassing of both water and hydrogen species. And once we consider degassing, it's possible that the situation may favor a much wetter LMO, but that's something that we need to see. So right now in our group, one of my graduate students, Arkadeep Roy, this is actually part of his doctoral thesis, where he is conducting experiments simulating lunar magma ocean crystallization. This is one of the experiments that he has done. This was conducted at half a GPa at 1275 degrees. And so as you can see, all the light gray part here, all of this is glass, and then all of these are different minerals, including plagioclase, which is the darker gray, and then there's iron-rich pyroxene, which are the lighter gray ones. And so what he will be doing is he will be measuring the hydrogen contents in the glass and these minerals at a range of pressure, temperature, and oxidation conditions to understand better how these partition coefficients vary as a function of these different variables, and also what is it for lunar conditions. And then he will be using that to model how much bulk hydrogen is needed to explain the hydrogen content in some of these lunar magma ocean products. So stay tuned for exciting results coming up. And so the conclusions from my talk today are that the moon is not bone dry. It has tens to hundreds of ppm of water, but then we need to constrain the bulk water content much better. And in order to constrain the bulk water better, we need to constrain the partition coefficient of hydrogen much better. And also from the first part of the talk, where we talked about how hot the moon is, given from the experimental data that we found about the temperature constraints at the core mantle boundary, likely a hotter moon is preferred in the range of selenotherms that we have so far. And of course, constructing a revised selenotherm using these temperature constraints at the core mantle boundary will help us constrain the interior of the present day moon much better. So thank you, and I'm going to end here, and I'm happy to take questions.
Thank you, Ananya. So I think we can go for a round of applause.